Hi everybody, welcome back to CENG 15. We are going to pick up more or less where we left off last time. I'm just going to up the mic here just a bit. We'll go up to maybe, I don't know, 6.5. That seems fine. We're going to pick up more or less where we left off on Friday. So we have introduced the idea of indexing and iteration inside of MATLAB. So the previous set of notes that we had developed over here read something like this. There's two ways to use indexing inside of MATLAB. If the indexing happens on the right-hand side of the equal sign, then the way that we interpret this, or the way MATLAB interprets it, is to go into this vector x, if that's the thing you're indexing into, find the position, maybe the row or the column inside of there, and tell me what number is there. It could be things other than numbers too, but for the most part, we're just going to work with numbers, I think, in this class. I don't think we're going to get to anything else anytime soon. The way that that looks inside of MATLAB is blah, blah, blah over on the left. We don't really care what's over there. And then somewhere over on the right, it looks like x of idx, or some variable parenthesis index. It doesn't have to be x idx, but we're going to use that a fair amount here. We'll see some variations on that today. The other option of indexing is if it happens on the left-hand side. That one usually looks just like this. There's not a lot of math that happens, because remember, the equal sign in most programming languages, including MATLAB, is an assignment operator. It doesn't indicate numerical equality. It says take whatever's on the right-hand side and somehow associate it with the stuff on the left, maybe store it at a location or create a variable or something like that. And so that's a way that we can have an existing vector or matrix or whatever and insert values into it. And that was a little bit new. That's not something that we could do in Excel previously. And in all of these cases, and there are some exceptions to them, but we're more or less going to take these as required. The variable has to exist. There are some ways that you can bend the rules and actually index into something that doesn't exist. But for the most part, they have to exist. Otherwise, you'll get errors about things not existing. The indices have to be integers. So there's only spot 1, spot 2, spot 3, right? There's no spot 1.5. There's no platform 9 3/4 on here. And the indices generally have to start at 1. And they have to be less than or equal to the number of elements in the variable. Again, there are some ways that we can do some tricks that make it access things that are outside of that, the end of the vector, end of the array. But for the most part, they need to be in that particular location, or I should say, in that particular range of 1 to however many things are in there. And where we got to, after a fair amount of work on Friday's class, was that this setup is more or less the way that we get started with indexing and iterations. So we start off with defining some kind of a sort of a setup feature. So here we wanted to plot, so we generated some x values. We typically have to pre-allocate something when we're using indices or indexing and iteration. Pre-allocating helps ensure that things aren't going in a funny order. It'll often throw errors if you've messed up one of the indexing or indices or something like that. And that's actually good because it tells you something that you expected did not go the way that you thought it should. Then we start the iterative loop with a for statement, and we define a list of integers, usually going from 1 to however many elements we need. We're going to see it doesn't have to be 1 to that number of elements. It can be a lot of different things. We'll see a variation on that today. And then we do the individual calculation at each of those indexed values within the for loop. And it'll always end with an end. And most of the time, MATLAB will autofill the end for you so that you don't have to worry about something like that. So what we're going to do today is take that same idea and apply it to the random walk generation, or the random walk simulation that we've already done in Excel a couple of different times, but now we're going to do it in MATLAB. Before we do it in MATLAB, we're going to kind of repeat it quickly in Excel, but we're going to do it in such a way that we're setting up the pseudocode to understand what's happening inside of MATLAB. So the setup is going to look a little bit different in Excel, but we're going to use a lot of the same features that we have previously seen. So I'm going to start some Excel up over here. Those are my notes. That's where we're going. That one. There's our blank. Move around. There you go. Okay, so the pseudocode of what we're going to do. Remember, pseudocode is a nice way to sort of set up what do I think is going to happen. Roughly, what's the outline of the code that I'm going to work with. It's usually written in such a way that it's human readable. It's not directly translated into code that the machine can read. It's more for us. So what does that look like for the random walk? I'm going to lay out the pseudocode here, and then we'll go over exactly what's happening in a moment. The first thing we're going to do is set the number of simulation steps. We did that previously in Excel by just generating a big long list from like 1 to 100 or 1 to 5,000 or something like that. We'll have to do something like that in MATLAB as well. We're also going to have to pre-allocate a vector for x and y. So remember, our step consists of a giant list of x, y coordinates, right? And after sort of each index that's in there corresponds to another step. And in this case, we're anticipating a giant list of x and y. There should be a number of elements of x and y equal to the number of simulation steps. Each simulation step gets stored inside of x and y. And we're going to see that here in a moment in Excel too. Then we're going to start the simulation. And so for each step in the simulation, what are we going to do? Well, this is the process that we had laid out previously in Excel. We're going to pick a random direction. Once we know that direction, we can use that to determine the change in the direction that we want, right? We can change by a dx or a dy. And then we calculate the new value of x as the old value of x plus dx, and then the same for y. That was the updating process that we did in the random walk simulation in Excel, where we had x sort of new over here, we did some generation over here, and we x old, some calculations in x new, and then the row below that we had linked the current value of x old to be the values of x new that we had calculated in the previous iteration. We still have to do something like that here, and we're going to see what that looks like. Finally, we have to store the values of x new and y new in the vectors x and y. And that completes our simulation loop. When we're all done, of course, there's the last part that we want, which is plot y versus x. And in MATLAB, that'll be a pretty straightforward plot function that we would have to do on there. Just as a reminder of what I mean by some of these quantities, when our particle starts off at a particular location like this, it was given by a set of coordinates. And we had defined those coordinates as the old x position and the old y position. That's where we had started. And then we can go in one of 4 directions. We can either go right, up, left, or down. And we had defined various changes, right? We had said dx, if we want to go right, dx is 1, and dy is 0. If we want to go up, dx was 0 and dy was 1, etc., etc. I'm not going to list out all of the other ones, but this was right, up, left, and down. And the formula that we had set up is the new position that we wanted, x new, was equal to the old position, wherever we were, plus that dx value, right? Whatever the change is that we had. And similarly, that y new was equal to y old, wherever we started, plus dy. And we would just run that dozens and dozens, well, hundreds and hundreds or thousands and thousands of times as we ran our simulation. That was the core. Remember, x old and x new, by the way, started at 0. So initially, this was at 0, 0. Because we always wanted to start at the center of our plot. We could have made it set anywhere. It doesn't need to be at 0, but that's where we set it to be 0. So now we're going to demonstrate in Excel what this looks like in MATLAB. So we'll look at each one of those pseudocodes, and then we'll also look in MATLAB to see how this is actually being done. So we can watch each one of these steps. We're just going to write out the steps initially here. Remember, indexing and iteration is going to be a big part of all of the problems that we have to solve going forward. We're not always going to write it out like this. The first few times we'll write it out a little bit more verbosely, and then we'll start kind of writing it faster and faster and faster. So it is important to keep an idea of what's going on. But as I'll show you in a minute, there are ways to then go back into MATLAB and check that that's actually what's happening. So we're going to generate some index values, x and y. Remember, the index values in Excel are just kind of along for the ride. They don't really mean anything yet. It's not like we have a real vector of index values, so I'm going to put them as light gray. We start off with the first part in our pseudocode, which is to pre-allocate a vector of x and y, which actually comes right after the number of simulation steps. So if we want to be specific, let's do those in exactly that order. We're just going to run 10 simulation steps right now, right? So we set the number of steps to 10, and now we pre-allocate those vectors. So x and y are going to look like a bunch of zeros of exactly the same length, the number of elements, as we expect there to be number of steps. So just fill all these in with zeros. In MATLAB, we have the zeros function to do that, but here we're going to actually fill in the zeros like that. We're also going to then start our for loop. We know we have to pick a random direction and determine a dx and a dy. So let's set that up the way that we had seen before, which was there were a couple of options for dx and a couple of options for dy, depending on whether we wanted to go to the right or up or left or down. So the dx here, if we wanted to go right, was 1, 0 is up, -1 is left, and 0 is down, and 0, 1, 0, and -1 for dy. We're still going to have to somehow tell MATLAB those are the options, right? That's the only possible pairings that we can have. Now we're going to think about what it looks like in order to go through an iteration here and use indexing in order to determine both the direction that we have here, the dx, the dy, as well as calculating the old and the new values for x and y. So to help us visualize, let's pick an index. The index that we start with is traditionally 1. Usually that's the first value that we pick. In this particular case, this is an example where that's not actually the best case, because the 0 are the best choice. The 0 that we have for x and y at index 1 is already correct. That's already the value that we want, right? This doesn't need any change because we want it to start at 0 and 0. So in this case, we're actually going to start at index 2, because there's nothing that we have to do in index 1. The x of 1 and y of 1 are already correct. We don't have to change those at all. So we're actually going to start down here at index 2. So that'll be our starting point, is down here. So what we need to do now is figure out, how do I do all of these steps knowing that I'm on index of 2? So some sort of indexing while I sit inside of here. Well, the first thing I wanted was pick a random direction. So to pick a random direction, the way that we did that previously in Excel was to pick a random index, right? We had used random between, and we said, give me a number between 1 and 4. And I'm going to classify 1 as right, 2 is up, 3 is left, and down is 4. So I'm just going to pick a 1, a 2, or a 3, or a 4. This is the first time where we've seen two indices, right? We've got a general index for where are we in the step, but we've also got this other index for which direction did we take. And we can have as many indices as we want. They're just variables. We can make hundreds of them if we want. Once we know that, we can go on to the next step, which is pick the dx and the dy. So here's our dx, and we'll put a dy underneath it. And we need to extract, using indexing, the correct value out of our dx and our dy variables. Remember, in Excel, this was using the index function, and we select our array, in this case our vector of dx values, and we say which one do we want. I want the third one, which in this case is h22. And there you go. And similarly, index into dy, and return the value that exists at random idx, and that will give us those. It is going to be something of a problem later that this dx is the same as this dx. In MATLAB, we generally don't want variables to have the same name, because if they do, they're going to overwrite whatever the previous value was. So this could be a problem later. Could be a problem later, having two dx variables. We'll address it later when we get to it, but it's worth pointing out that eventually that could be a problem. Then we go on to the next part, which is the calculation of x new and x old. So what I'm going to do is extract the old values and then calculate the new values. So I'm going to have x old here and y old here. How do I get the old values of x and y given that we are starting off at index 2? Well, the index of the old values is always one less than wherever we are right now. So the old values, if I am at 2, the old values are the ones at 1. If I'm at 4, the old values are the ones at 3. So I can take this existing index and subtract 1 to get the old values, because those are the ones right up above me. So the old values, I would go into the vector that I've got over here, my vector of x's. And which one do I want? Well, I want the one that we're currently at, but minus 1. Right? That's the one that we had previously done, is the one right before us. So we subtract 1 off of there. Similarly with y old, we say I'm going to index into y. Which one do I want? Well, I want the current index that we're off now, but one previous of that, one above that, right? One prior to that particular index, because those are the old values. The calculation of x new and y new, this one is at least a little bit more straightforward. We take that old value of x and add to it dx, and we take that old value of y and add to it dy. Now we've got our x new and our y new. So right here, when we calculated these values, that was applying these functions that we have originally defined up here at the top. There's our x new and our y new. Now in Excel anyway, there's not really a way to do what we currently want to do. What we want to do is take these two values and paste them in. So let's say equals, put these values in row something. And which row do we want? We want it in whatever the current index is. So we'll use our concatenation here just as a little reminder for us of A, how that works, but also where do we put these things. So these are coming from idx minus 1. These are coming from idx minus 1. And these values are now going into the actual idx, right? They're going into whichever row we want. This is not a process that we can do in Excel particularly easily, but we can at least demonstrate what's going to happen in MATLAB. So that's sort of one iteration through here. What MATLAB can now do with indexing is say, okay, take these values and paste them in here into our second row. What does the next step of the iteration look like? The next step of the iteration is the index increments by 1. It'll go from 2 up to 3. A new random number is generated, which it actually is, but let's sort of run this again just so we get a different random number. It'll recalculate the dx and the dy for that random number. It'll grab the old x and the old y, which notice these are now the ones that we had just calculated previously, and it'll recalculate a new x and a new y. And then we want MATLAB to say, all right, take those values and put them into row 3. Increment again to idx is 4, put these values into 4, increment to 5, take these values and put them into 5, etc., etc. This is why I only did 10 of these, because the copy pasting part here is a little bit tedious, right? If I'm doing this by hand, I don't want to do this more than about 10 times because it's just going to get kind of boring. But this is exactly what MATLAB is going to do, right? We are setting ourselves up to be sort of a manual MATLAB right now, right? And then it'll complete to however many indexing values that we want. And then we'll select both of these and go plot them, but I'm not going to plot them in here because we're just doing an example. So that layout sort of highlights what is similar to the things that we've been doing in Excel, in the sense that we can still use indexing, we can still use the calculations in the same format that we did before, we can still go in and look up values out of vectors and that sort of stuff. The one that we can't do is this one. Right, this is brand new. We've never been able to do that before, and that is something that will speed this process up in MATLAB. So this is new to MATLAB. We've never been able to do that before, where we can copy paste values as they're generated sort of one at a time and store them in a vector somewhere. Again, it's possible inside of Excel to do something like that, but it's not clean. It's not very pretty to do something like that. So this is what we're then going to go do over in MATLAB. So I'm going to just pause here for a moment, A, for you to catch up if you're watching a video, if you're watching this live, but also B, if you've got any questions or anything, now's a good time to knock this out because we're going to go do this in MATLAB here in about 2 minutes. So I'm just going to wait for about maybe a minute or so in case anybody's got any questions. Okay, no questions, so let's flip over to MATLAB, and this is what we're going to do over there. So the first thing we're going to do, I've given myself a new folder over here, right? All of my lectures are being built up in folders. I would strongly encourage you to do that at least for your homework, right? Give each of your homeworks a new folder so that we don't run the risk of having the same things labeled the same way in the same folder. So I'm in here in lecture 9. I'm going to give myself a new live script. We are going to look at other forms of scripts here in a little while, but right now we're going to stick with live scripts. And we'll have our live scripts. I think I'm going to switch them instead of left-right. I'm going to do them top-bottom so that plots show up along the way. So remember our pseudocode. We have to do the same idea that we had done previously. The first part was set the number of steps. So the number of steps that we have previously was 10. So this is the number of simulation steps. We can eventually change that. I've got a little bit of code here, so I'm going to go ahead and save this so that I don't lose it. So this is lecture 9a. The next step in our pseudocode was to pre-allocate vectors. Remember, pre-allocation in MATLAB is usually done with the zeros function. Sometimes the thing that goes inside of here is 0 of something else, or a size of something else. We don't really know the size of anything else, so we can just tell it, I would like 10 rows of zeros and 1 column of zeros. So this is 10 by 1 zeros. If we wanted to with y's, we could do the same thing, right? We could do this as also 10 by 1. But both of those, notice they have a logical connection to the number of steps, so it would be nice if when I change this in the future, if I go to 15, I don't have to come down here and type each one of these and change them to 15. So instead of saying 10, although logically that is correct, let's use n steps. That'll ensure that I've got a number of rows equal to the number of simulation steps that I've got to use, or that I'm going to use. Stop auto-popping. Thank you. So it'll happen to be 10 by 1 right now, but more generally it'll be n steps by 1. Of all zeros, right? Just like we saw over in Excel. The one thing that we don't have to do in MATLAB that kind of helped us a little bit in Excel was to visualize that column of indices. They're always there, right? They're baked into those variables that we don't have to do anything to get those indices to show up. Notice we didn't really use them in the previous one. In the Excel example, they were just along for the ride to help us visualize things. Now we start our iteration. Remember, the iteration always starts with a for, and then we define what is our indexing variable. I like IDX. I is another good one. J is another good one. Some people use II as their indexing variable, whatever you prefer. Typically, this would look something like 1 to length of a variable. We could definitely do that. Remember that we didn't want to start at 1, we wanted to start at 2, because the first entry in both the x and the y are already correct. They're 0 and 0. That's not part of our simulation to go in and change those. They should stay at 0 and 0. Other things that we could do here, and I think, ways that I will probably do this is 2 to the number of steps. There's nothing wrong with saying 2 to the length of x. The length of x is going to be the same as the number of steps because we have how we defined it up here. So either one of these would be okay. Personally, I like 2 to the number of steps because to me that reminds me, what am I iterating over, right? I've set a number of simulation steps. I need to iterate over each one of those steps. So it could equally be 2 to the length of x or 2 to the length of y. Those would both be okay because the lengths of both of those are going to be the same as the number of steps. But I like 2 to the number of steps because it reminds me what I'm trying to do. MATLAB is going to automatically complete my indexing or my end statement for me. And now I need to do that random number generation in order to pick a direction. Remember that the vectors of the 1, 0, minus 1, 0 for all of the dx's, and similarly for dy, those never changed. So there's no need to put those inside of the for loop, although it wouldn't hurt anything if they were in there. It's a little bit sort of more logically straightforward if I move them outside of the for loop because those are constants. That selection of data never changes. So remember, if we went 1, it was to the right, and then up, and then left, and then down. And similarly for the dy's, it was 0, 1, 0, and minus 1. Remember, these go in the pattern of right, up, left, down for each one of those. So I'm defining these outside of the for loop. It wouldn't hurt if you defined them inside of the for loop. It would just sort of redefine them each time, which is fine if that's what you wanted to do. Now we have to generate our random index, right? The variable idx will exist. So there will be a variable that looks like idx is 1, and then idx is 2, and then idx will be 3, and then idx will be 4. But we don't have to define that. It's not a variable that we need to create because we already created it right here. So that step is already done. We don't have to do that. That's part of the for loop. But we do need that random index. So we saw in Excel that we defined it as rand idx, and the random number generator that we want inside of MATLAB is given as rand I, which is an integer. And so the argument here is 1, 4 inside of a set of brackets. This will give us a 1, a 2, a 3, or 4, right? Exactly like it was done over in Excel. Now we have to do the indexing that we had done previously, right? We have now generated a number 1, 2, 3, or 4. We need to take that as an index and go into the dx and grab the appropriate value there, and go into the dy and grab the appropriate value there. This is where I said it's not a good idea to use the same variables. So conceptually what we would like to do is define dx as dx of random idx, right? This on the right-hand side, remember that's following the indexing pattern. There's an indexing that occurs on the right-hand side. So the way to interpret this is go into the variable dx, which is up here, and tell me what the value is at the location rand idx, which is either at location 1, location 2, location 3, or location 4. The problem is we've got a dx here and a dx here. MATLAB won't complain about that. It can do that. It's okay with it. But we shouldn't call it the same thing because we want to leave these dx values alone, right? Those are constant. They never change from loop to loop. So we should come up with something else. So we can call this dx anything that we want to distinguish it from the other one. So I'm going to call it this dx. Right? It's the current one that I'm working on to distinguish it from the selection of all possible dx's. And we'll see another way to do that here in a few moments. Similarly for dy, I'm going to call it this dy rather than dy because I don't want it to overwrite old values. And I'm going to index into dy from the same location that I did for dx. That way I'm always drawing sort of pairs of dx and dy. Now I calculate values. In order to calculate values, I have to get the old values first. So this was sort of our random generation. So this was pick a random direction. This step here was to determine dx and dy. right? We're just going in the same pattern that we had laid out in our pseudocode previously. And now we wanted to calculate things like x new are equal to x old plus dx. Right? That's the type of calculation we wanted to do. If we wanted to follow the pattern that we did in Excel, the first thing we would do is extract the old value of x. So I would say something like x old is equal to what? Well, remember over in Excel, we went and looked up the value in the x vector that we had, but minus 1, right? We went to the value just before the current step that we're on right now. So if I want to index into x, I'll start with x of something. That's how we index into something. Where do I want to go? Well, I want to go to the current index that we're on, but subtract 1 from it, because I want the value that's right above it. Similarly for y old, I go into y and say, give me the value of y at index almost, but index minus 1. Right? Go up a little bit higher than that index. Now we can calculate stuff. We can say x new is equal to x old plus this dx. And similarly, y new is equal to y old plus this dy. Notice that we're not saying plus dy, and we're not saying plus dx. Right? We're not doing that because the dx and the dy are vectors, and we don't want to try to add a vector to essentially what is a scalar, right? Each of these are individual numbers. We just want to add this current value of dx and this current value of dy, which we've called this dx and this dy. And remember the last step that we had? This was the part that was annoying in Excel, which was store x new and y new in the vectors x and y. Right? We've now calculated them. We want to make a note of what we had calculated. We don't want that data to just disappear. And so what we will say, similar to how we did with indexing on the right, we use indexing on the left. So where do I want it to go? I want it to go into position IDX. That's our current value, right? These are our new values. And so I use indexing on the left to make an assignment. The current value of x that we want is the value of x new that we just calculated. And the current value of y that we want to store is equal to the value of y that we just calculated. So those are all of the steps that we did inside of Excel. This step, this is what we did by hand. Right, just a moment ago when I was copy pasting row at a row after row after row after row, that's what we're doing right here, right? We're calculating the stuff, we're pulling from that on the right, and then the indexing is happening on the left, so that means it's taking x new and inserting it into the current position of x, defined by x of IDX. And then we needed our plot. The last thing that we needed was plot xy, and we'll plot with a black line, because that's what we were using previously. Right, same idea as what we had before, but it looks a little bit different. There are a number of different things that we could do to clean this up, to make it look, to really just use different tools in order to do the same thing. And we're going to look at those in the latter half of today's class. And then we're going to actually keep staring at this on Wednesday's class as well, so that we can learn even more new ways to do this. But let's take a look at the plot here. Let's go ahead and run that. So you can see that it printed out all of the values of this dx, right? And the reason for that is because I forgot up here to put a semicolon after dx. So I'm going to put a semicolon there so that it stops printing those. And then I'll get my plot under here. The plot looks a little bit funky because we're only going about 10 steps, and so there could be a lot of going back and forth over the same positions that we were before. One thing that we can do to help that is up the number of steps. So instead of 10 steps, let's take 100 steps. And if we run that with 100 steps, we can see now we're starting to get a plot that looks a little bit more like a plot should, right, of our random walk. We've seen these random walks before. I'm going to show you a couple of ways to clean up plots to make them look a little bit more, I guess, I want to say neat, but when I say neat, what I really mean is they're a more effective means of communicating the results of your calculation. So neatness is really a choice of communication here. That's what I mean when I say make it look neat or pretty it up a little bit. So one of the things that we can do is fix our axes. So that's something that we saw in Excel. There was a menu that we went into and we could set the min and the max. You can do that in Excel or in MATLAB as well with the xlim and the ylim functions. So maybe I want to set this to be always minus 10 to 10 for the x and the y to always be minus 10 to 10 as well. So xlim and ylim are fix the x-axis and fix the y-axis. Right, and so that will at least get us so that the plot stops changing, right? As I run this script more and more, the plot kind of looks the same, right? It's the same window, and we can just see that the walk itself is moving as we go. Something else that we want to do is set we wanted each one of those boxes to be square, right? They kind of look like rectangles right now. If you say axis square, that is a 1-to-1 or a square aspect ratio. And that will make the visual length of the x-axis the same as the visual length as the y-axis. It doesn't change the numbers, it just changes the scaling on the way that it's drawn. And that way each one of these sort of imaginary grids that we've got on here looks more like a grid, right? A nice square grid that we've got. One other thing that we can do when we set the axis limits to go through 0, notice the axes numbers, the tick marks and stuff, they don't move to the middle like they did in Excel. There are ways to do that in MATLAB, but they're kind of a pain in the neck. Usually what I like to do is just set something up like this, and then if I want to see the zeros for x's and zeros for y's, I just draw them. So one way to draw them, there's a command in MATLAB to draw horizontal lines as x lines, vertical lines as x lines. And so we can say, draw me a line at 0 and make it a black dashed line, and draw me a line at, well, no, actually it's y is equal to 0 and also a black dashed line. So these are optional. They don't really add anything to the plot, except they help it be a little bit more obvious to the reader or the viewer, or in this case the grader, exactly what's happening in your plot. This is more than enough on any of your homeworks that you have to turn in. You don't have to try to move the actual axes to be in the middle. Running it something like this is perfectly fine. And it's pretty fast once you remember the x line and the y line. They become kind of second nature, and it's a little easier to remember those than it is the other commands to actually move the axis. We did want to plot the endpoint a lot of times in these random walks, so we can do that too. We have seen previously that when we want something to show up on the same figure, we use a hold on and a hold off command. So we say hold on here, we put a figure up ahead of it, and then we plot wherever we wanted. So we wanted plot, and all we wanted was the last point in each one. There is a special keyword in MATLAB called end, which allows you to go right to the end of any array, any vector. And that's helpful here because all we want is the last one, right? We just wanted to plot the last value. So we can say something like x of end and y of end, and it'll just plot that pair at the very bottom. And that's a little bit more convenient than extracting them, although you could, of course, extract them if you wanted to. And then we'll set the marker to red, circle, with a red face color as well. And so there we've got our dot on here. Go away, a little auto update. Oh well, I guess it's stuck for now. That's all right, it'll go away on the next one. So now you can see we've got our little red dot up here and an annoying pop-up window that is stuck on here that's stopping us from seeing this. Maybe it'll go away over here. Nope. Clear all output. Nope, it just really likes it. It's just stuck there for now. It'll go away later. At any rate, this is pretty close to where we were at the end of our first Excel random walk generation. We did a little bit more work with measuring dimensions, those displacement values, but I'm going to leave those for you to work out on your homework. We're not going to go over them right here, because what I want to go over as we did in Excel, are the other ways that we can do this random direction stuff. So we had started off with this indexing method in Excel, and then I had shown you a couple of other functions that can do something similar. One was a choose function, where we sort of list out, here are the options, and give me option 3, give me option 2, something like that. We can do that in MATLAB, and also we can do a very powerful method in MATLAB, which is an if statement. And we saw that that looked kind of ugly in Excel because we had to keep nesting ifs. That looks a lot more elegant inside of MATLAB, so we're going to look at that really quick. So we're going to leave as much of the rest of this code as the same as we can. And as we did in Excel, we're going to look at two different ways that we can do this sort of indexing here. One with a statement and one with an if statement, a choose statement. So I'm just going to pause for about a minute or so in case anybody's got any questions or needs to catch up, and then we will move on after that. I'll try to show as much of this as I can. Okay, so let's look at the other ways that we can do these random directions. So I'm just going to take this entire script, copy paste it into a new one over here. We want basically all of the same behavior, but let's do it without this indexing that we have here. So let's eliminate this dx and this dy, and we'll determine the dx and the dy a little bit differently. So here we're going to use a switch case. So a switch case behaves the way that we saw the choose function works in Excel. So this is like choose in Excel. But it's, I think, laid out a little bit more intuitively. So the way that you set up a switch case is you define the condition on which you want to then pick from cases. So you say switch, and then what do I want to switch on? Well, I want to enumerate the different cases which correspond to different values of random IDX. There's a 1, a 2, a 3, or a 4, right? There are different cases of what to do in the event that random IDX is 1, 2, 3, or 4. If you hit enter, MATLAB should auto-complete this to say end, and now you can start defining cases. And cases are defined starting as exactly that, right? You just say case followed by what is the value of random IDX for which you would like to describe a case. So we can say case 1. This corresponds to going right. That's case 1. If random IDX is 1, that means go to the right. If we go to the right, that means dx is 1 and dy is 0. And now you can enumerate additional cases. You can say case 2, which is up. That corresponds to dx is 0 and dy is 1. Same thing for 3 is left, and same thing for 4 is down. You can probably guess what goes in each one of these, right? It's going to look something like a dx and a dy. Just depends on which direction you want to go. So I will set these, if we go left, it's dx is minus 1, dy is 0. And if we have a case of going down, we have dx is equal to 0 and dy is equal to minus 1. So this can look a lot more readable, right? It's a little bit more clear when I'm looking at this. There are only 4 cases of what I can do, and those 4 cases are set by the value of random IDX. So random IDX has to take on a value of 1, 2, 3, or 4. There is another case that you can use as sort of a catch-all. So there's one called otherwise, and then you can put other stuff here as sort of a catch-all. But we don't really need that in this case because we know we're always going to get a 1 or a 2, a 3, or a 4. But depending on what your simulation is, there may be only a couple of cases that you're interested in, and if something other than those cases happens, you always do the same thing. That's where you can use an otherwise case. But here we don't need the otherwise because there's nothing else to do, right? It's only a 1, a 2, a 3, or a 4. Now we don't have vectors of dx and dy, we have actual scalars of dx and dy, and so our code down here can look even a little bit more readable versus the way that we wrote it by saying dx and dy here. Now we don't have that problem of there's 2 dx's floating around and there's 2 dy's, right? We don't have the vector of all possible dx's and then the particular value of dx that we chose here. We just define the values of dx and dy as we need them using a switch case. I like the switch cases. Whenever I can use a switch case, I like to use it because for me it's very human readable. It's clear what the cases are, it's clear what's making the choice. There's no comparisons that I have to make. It's just going to be one of those. And if anything else happens, then I need the otherwise statement. So that's one option. I like the switch cases. If we run the script a few times, we'll see, yeah, sure enough, it's doing exactly what we thought. Not much that we have to change for something like that. The one limitation of a switch case, is it can't do comparisons. So it can't do things like greater than or less than or equals, well, it actually is doing equals to. It can't do greater than or equal to or less than or equal to or not equal to or something like that, right? It can't do numerical comparisons. You just have to list the cases and it picks one. That's actually pretty powerful. There are a lot of things that can get done just with a switch case, but there is another option which allows you to make these comparisons, which isn't necessary for this particular example, but we're going to use it a lot on our upcoming simulations. So I'm going to show you that one as well here, and we'll practice it a little bit more later. So let's take exactly that and see a different way to do it. So now instead of determining dx and dy using a switch case, let's use if statements. And if statements are the same as what they were in Excel. They're just a little bit more easy to interpret inside of Excel or inside of MATLAB. There are a few different syntaxes that we can use for ifs. I'm going to show you one of them, and then we'll talk about the differences between them on Wednesday. We'll set up the other way that you can do an if statement on Wednesday to compare. They actually execute differently in code, so we will look at the 2 different methods that we want. So we can start with an if statement and say if random IDX is equal to 1. Note the double equals here. This means that you're doing a numerical comparison. The double equals is different from the single equals. The single equals, remember, is an assignment operator. The double equals says if random x, if the value of random x is numerically equal to 1. That's different than saying if I had done just a single one here, this is an assignment operation. That would pretty much break our simulation because that's saying set the value of random IDX equal to 1. And that's not what we want. So if statements usually use a double equals if they're going to do some kind of an equals comparison like that. So if it's equal to 1, then you must be going right, and we can kind of define things as we did before. So dx is 1 and dx or dy is 0. Then we want to say, well, what are the other cases? This is where there are different ways to do if statements. The way we're going to do it here is to say else if. So else if says, okay, if that one failed, now check this one. So if random IDX wasn't 1, then check for me if random IDX is 2. This corresponds to going up, so we would say dx is 0 and dy is 1. And then we can just keep piling these on, right? For every other comparison that we want to make, we add another else if statement. And then finally, else if random idx is equal to 4, this corresponds to going down, and dx is 0 and dy is minus 1. We close it with an end. As I said before, there are different ways that you can set up if statements. This is one of them, and the reason that I set it up like this is because it's similar, at least in appearance, to the switch case that we had over here. You just enumerate the 4 cases, and then you say end. This will work just fine. There's nothing wrong with this. Oh, I guess I have to save it. I'm not going to bother saving it right now. This will run the same as the switch and the same as the indexing, but there are other ways to define these cases with if statements, and that gives it more flexibility, right? The indexing and the switching are kind of fixed. The if statements can be very flexible. You can do lots of different comparators for those. So I'm going to wrap it up here because we are at 12:51. Everything that we've done here is about as far as you need to finish up the rest of the homeworks. Everything that we're going to do on Wednesday and Friday is not necessary for the homeworks. We're just going to look at other variations on this. What we've done right here is enough for problems 4 and 5 on homework 2. So you should be good to go on that. I will see you on Wednesday. I'm also going to send out an email with a little survey checking office hours because we're about 3 weeks into the class now, starting week 4. I want to make sure those times are working for you. So if you have any suggestions on new office hours, there'll be a survey a little later today. So have a good one, everybody. Stay safe out there. I'll stick around over in Canvas chat if you've got any more questions. Otherwise, I will see you back here on Wednesday. Have a good one all.